Thanks everyone for coming to the last episode of the One World ABI seminar for this semester, this season. We're very happy to have two speakers who were giving posters at Bayes and they've been upgraded to give 30-minute talks. So 25 minutes and then 5 minutes for questions. We'll try and take questions live as well from both the audience here and then also the virtual audience. First, we have Filippo Pagani, who's going to talk about approximate Bayesian fusion. It's all yours. Have a seat, Fred.
Thank you very much. Hello, everyone. Thank you for having me. I'm Filippo Pagani. I am a postdoc at the University of Warwick on the Grand Ocean, and I am working on, in the context of like Bayesian fusion, more specifically on approximate Bayesian fusion with Adam Johansen and Gareth Roberts. This talk is in the broader context of distributed inference, distributed Bayesian inference. So what I'm just going to quickly go over that in case not everyone is familiar. Distributed inference is, so normally when you're doing inference, you have you put the data together, as you can see, like on the left-hand side of the slide, you put the data together, you have the joint data set, you do your inference on the joint data set, which could be, for example, running your random walk metropolis on the joint data set, and then you get a sample from the joint posterior. Okay, and this is what people normally do, and it's the correct thing to do, but sometimes that is not possible. For example, because there are regulatory constraints. For example, the NHS has every hospital has a different database, for example, and maybe they can't share the data with each other because of privacy reasons. Another example could be that the data is just too big to be hosted on a single machine. There are probably other reasons as well. And in any of these cases, you can't put it together and do inference normally. So what you can do instead is you do inference separately for each subset of the data, and then you got to put the inference together somehow. Now, if you're not Bayesian, this is not a big problem because you're basically putting together like point estimates. But if you're Bayesians and if you care about distributions, then putting together like distributions or like samples from distributions, it's not trivial. It's not trivial if you want to put them together and get the true posterior at the end of your process pipeline, say. For example, this is a small example to show you that it's not trivial. This is just a linear regression, okay? You have, well, two coefficients, even though we're just going to concentrate on one on the intercept. You have 300 data points divided on 3 cores, okay? And let's assume you run Metropolis Hastings on the 3 cores separately. What you get for each core is a sub-posterior. So the red, the blue, and the green ones are the sub-posteriors from the 3 different cores. As you can see, they're not quite the same, right? And if you want to put them together naively and you just pool the samples together, what you get is something like the dotted purple line that you see, the low line here in the picture, which is very different from the dashed black line, which is the KDE from the sample run using Metropolis Hastings on the full data set. You see, they're quite different, so it's not a trivial thing to do. In general, in the literature, there are, let's say, 2 methods that are opposite end of the spectrum. Opposite ends of the spectrum. One is consensus Monte Carlo, which is scalable, approximate, but the approximation error can be large. And at the other end of the spectrum is Bayesian fusion, which gives you basically an exact sample from the true joint posterior of the data, based on the data. So these are the 2 extremes, okay? Let's talk about for a second about consensus Monte Carlo, so that I can give you a better idea of what it does and why it works. Basically, consensus Monte Carlo is so simple because it assumes that every sub-posterior is normal. It's normally distributed. And basically, if that is the case, then when you put them together, you just multiply the sub-posteriors together. And because they're all normal, you can just complete the square and obtain the joint posterior, which is going to be, once again, a normal distribution with a certain mean and a certain variance. And this works great as long as the sub-posteriors are actually normal. If the sub-posteriors start deviating from normality, then what you get, the joint posterior that you get from consensus Monte Carlo and the true posterior become different, like the difference grows quickly. So this is consensus Monte Carlo, and it's the sort of like the scalable extreme of the spectrum. Bayesian fusion, which is the method on which my work is based, is at the other end of the spectrum. My work is approximate Bayesian fusion, and we would like it to be somewhere in the middle to get the best of both worlds, in a sense. So we would like it to be scalable. It is approximate, but also it's a controlled approximation. But what is Bayesian fusion? Bayesian fusion, to define that, let's talk about the fusion problem a little bit more in detail. The fusion problem is when you have different posteriors, like when you, as I said, the posterior of interest is proportional to the product of the various sub-posteriors from your data shards. Yes. Absolutely. Yes, absolutely. So your posterior is proportional to the product of the sub-posteriors, okay? Now, sampling from F is generally not possible directly, but what you can do is, if you can get a sample from your sub-posteriors and you can run a double Langevin SDE with certain, just a double Langevin SDE, then if you can do those things, then you can construct basically the distribution, the joint distribution G, which is the joint distribution between the initial points from the various cores and the final point, Y. If you can construct this, then you can throw away everything but the time t marginal of this distribution. So the Y samples, you can throw away everything but the Y samples, and those Y samples will be a sample from the true posterior that you wanted to target. Okay. This expression seems a little bit complicated, but it's actually not that complicated because things simplify away, and I'll show you in a second. Okay, how do I probably have to just do that. Yeah, okay. So as Frank van der Meulen said yesterday, in every presentation, there should be always at least one simple proof. This is it. This is the simple one. Basically, I mentioned a double Langevin. What is this thing? In case not everyone is familiar, it's very simply like a Langevin SDE without the 1/2 scaling factor in front of the gradient, or and without the, alternatively, without the square root of 2 in front of the noise. Yeah, it's just that, very simple. This thing has stationary distribution FC squared, okay, rather than FC. And okay, and let's keep this information here for a second. If people remember, the global balance condition is quite fundamental to MSMC. So basically, when you take the integral, when you take the integral of your stationary distribution times the transition kernel of something, and this is a transition kernel of the double Langevin, you get, once again, the stationary distribution. Okay, this is another well-known thing. And as I said before, when you create this big joint distribution between the X1 to C and the Y, you can throw everything away and only keep Y, right? In practice, if you integrate out the X variables, you can basically, right now, the first line of the proof is I've substituted the definition of G from the previous slide. That's it. The second line, I've broken up the integral because for different XC, the integrals are independent. And then the third line, I get there by just applying global balance here. and basically the integral turns out to be fcy squared. It simplifies, and what I get is exactly the posterior that I was after, the posterior from the full data set. This is the basis of the method, basically. If I had to summarize the method, so this tells you why the method works, right? If I had to summarize what the method does, basically, it's quite simple. If you don't want to go into details, you just take a sample from the subposteriors, okay? You simulate, starting from each of the samples, you simulate a system of SDEs until time t. Once you get there, you reweight the trajectory of the system and only keep the time t marginal. That is a sample from the joint distribution. The distribution, the posterior calculated from the full data. This is what I mean. So it's literally just 4 steps. This with the pictorial representation, what you're doing is, so ignore for a second what's on the left-hand side. But on the right-hand side, you have, here you have the course, okay? And let's pretend we're in 1 dimension, so like the vertical dimension. Let's ignore it for a second. What you're doing is you're taking 1 sample from each subposterior, and you're fusing these samples together with Brownian bridges until they coalesce on the same number at time t. Okay, and this is essentially the system of SDEs that you're simulating, and that sample that you get at the end will be from the distribution from the full data set. Going slightly more in detail, this system of SDEs that I'm talking about is this one here. Notably, so these SDEs are moving forward, but they have to coalesce at time t. How does that work? Because you have the mean here, the mean calculated across the course, which is as if you had like another red line, another red Brownian motion line here in the middle, which is the line that pulls every other line together, and makes sure that everything coalesces on the same point at time t. So this is simulating the system of SDEs, and then at the end you reweight the trajectories by this complicated expression down here. But we don't have to go into details about what it means and where it comes from, let's say. But I wanted to put it there because basically this thing, there should be a square up here. This is a typo. This thing is relatively easy to calculate. It's basically like the kernel of a normal distribution. This thing is much more difficult. The right-hand side, like the term on the right, is basically the bottleneck of this algorithm, which is a fantastic algorithm, but this is the most expensive part of it. And basically, to get an exact sample, you've got to calculate this by simulating Brownian bridge paths using the layered Brownian bridge construction from a paper, which I should have cited, from Alex Pescos and other people. That is very expensive because you need bounds on things, and it takes a lot of computational time. What I'm doing personally, and also the function phi is not the simplest function. As I said, this integral is expensive. The function phi is the following. So basically the 2 norm of the gradient of your subposteriors plus the divergence of the log Hessian. So it's literally just the sum of the diagonal elements of the log Hessian. This is not the simplest function to evaluate either. In the sense, I mean, you can evaluate it, but it's expensive to evaluate. So what I'm doing on this project is I've basically approximated the integral with the simplest thing I could think of, so the trapezium rule. This makes, obviously, this is a discretization. It introduces some bias, but at the same time, it makes the algorithm a lot simpler and much faster. What this means in practice is that when the particles representing a sample from each shard are fusing together along the Brownian bridge paths, what we're doing is we're dividing the path in time windows, so of size tj minus 1, and we're approximating the trajectory of the Brownian motion with a line. It's super simple. yes, so this is the basis of it. Let's look at some results and look at some nice figures, which I'm sure everyone will appreciate at this hour. This is a simple simple beta example. It's an 8-dimensional one with 5 shards with 5 different sub-posteriors to fuse together. I only did 10,000 samples. As you can, I've run fusion, and the blue histogram corresponds to sorry, when I say fusion, I mean approximate fusion, approximate Bayesian fusion. The blue histogram corresponds to that. And I would say orange, I'm not exactly sure what color this is. Red. Yes, that. That is a sample from just a very simple Metropolis Hastings algorithm run on the whole data set. So I took these to represent the Monte Carlo truth, and they're quite similar. And they're also both quite close to the black line, which is literally a beta 5.2. So it works quite well in practice. In the sense that if people were worried that it was a biased method, yes, it is biased because it's not exact, but also if you take a small step size, that really doesn't show up very much. I just wanted to compare it quickly to the other method I mentioned before, sequential Monte Carlo. So if on the same beta sub-posteriors, right, and you try to join them together with consensus Monte Carlo. Maybe I said sequential Monte Carlo. I mean consensus Monte Carlo. This is what you get, which is nowhere near the actual beta 5.2. I used 1 million samples here, which is a lot more than 10,000, because I wanted to be sure that at the end, at the right end of it, it was dropping, because that's what it looks like. But yeah, basically, it's not even close. The other problem with consensus Monte Carlo is that if you take even more samples, it doesn't matter, because this is the distribution that it's returning. It doesn't get closer to the actual beta 5.2, even if you have more samples, right? This is it. So biased, but quite different types of bias, yeah, between approximate Bayesian fusion and consensus Monte Carlo. This is another example. This is a 2D Rosenbrock distribution, which I probably should have put an introductory thing, but basically this is what it looks like. It's a banana in 2 dimensions. Okay, these are the 2 marginals. And I used more samples here, like 2 million samples and still 5 shards. I think the algorithm is doing a pretty good job. The thing though, if you look very carefully, you can see some of the bias coming out, because if you look here at the top on the at the mode of the distribution, the truth seems to be slightly lower than the fusion result. And you can actually see it slightly better on the bottom plot, where fusion seems to be slightly higher on the mode as well. Well, this is the bias showing up, but I think it's pretty small. And also it's quite normal for a particle-based method to not be able to estimate the tails of the density super well. But anyway, so these are the 2 marginals. Now we can look at like 2-dimensional plots of the whole distribution. I put them like one after the other because I could flick through them and actually show you the difference, because I think you can see it quite well this way. So this is basically, this plot shows the contour lines of this Rosenbrock, the fused Rosenbrock distribution. And this is the same thing about a random walk sample from the same thing, joining the data and then doing the random walk. As you can see, like the thing that really changes is basically mostly the outermost line, the purple line, okay? And that is the confidence contour corresponding to the 99.9th percentile, okay, which is quite far away in the tail. I think this level of bias is okay. It's not too big. And then for comparison, this is what you get if you use consensus Monte Carlo. So not quite close. Yeah, so yeah, this is what I had to show you. And basically to conclude, approximate Bayesian fusion is a promising new method. we're trying to combine the pros of both consensus Monte Carlo and Bayesian fusion, hopefully with basically none of the drawbacks. And these are preliminary results, right? There's a lot of work to do. For example, I haven't, one thing I am working on, but I haven't put in the presentation is I'm working with a logistic regression because I am trying to scale it up, and it's not a problem. The problem is when you scale things up, then you have to have a good way to tune them. And basically I haven't had enough time to figure out a good automatic way to tune this, but I am working on it. Yes, and then there's obviously a lot of work to do on the theory side in terms of like error bounds and that sort of thing. And this is just about the current state of the algorithm. In general, there's a lot of things that one can do to actually improve its efficiency and scalability and so on. For example, there's another paper on fusion from Ryan Chan and other people, and the usual people involved in fusion. And it's a divider and conquer approach to fusion, and it works. It makes fusion, like exact fusion, a lot more efficient, and I imagine it's going to work even better here because yeah, things are already much faster, so this is going to make them scale even better. Yeah, so lots to do, but like promising results, I would say. And these are some references that I have, so thank you for your attention.